Hello and welcome to Lecture 26, where we're going to cover Section 8.2 on the topic of center of mass. The reason we're covering a section called center of mass in a chapter it's all about rotational dynamics is we need to understand that objects that rotate have dimensions and they must have a center. This is different than when we've talked about translation up to this point, whether it was energy, momentum, or just plain old kinematics, because at that point, if it was just a particle, it didn't really have a center because it just moved as one unit. But here, if something is going to rotate, that means it's got to rotate about some point. We've kind of already introduced the idea of an axis of rotation and so on, and we're just building on that. We're just giving a formal definition to the center, okay? And it turns out that the center of mass is kind of a problem in its own right. It can solve simple problems involving the center of mass, and it even relates back to conservation of momentum. So let's see how that all shakes out, okay? So let's look at our one key term here, which is just center of mass. That's just the title of the section. All right, it is the balance point of a system or object. That's a good practical way to think about it. Okay, if I was to hold something on my finger, I would hold it at the center of mass and then it would balance on my finger. So the center of mass, shortened as COM, has equal effects of mass on both sides along a particular axis. So when we talk about the center of mass, it's a coordinate, so it has a x, y, and potentially z coordinate, usually x and y at most, and that's the balance point along those different axes. Okay. This does not mean, this is a common misconception, this does not mean that there is equal mass on both sides of the center of mass. Take a broom, for example. If I hold a broom, I need to find that balance point. It's going to be pretty near the head of the broom. There's actually going to be more mass on the head of the broom, which is closer to that balance point, than there is in the entire handle. It's just that the handle has just as much effect on the balancing because the mass is more spread out. So anytime you have more spread out mass, you don't need as much to balance. All right, so center of mass does not mean equal mass on both sides. Just remember that and think of practical ways of visualizing that for yourself. So for objects, the center of mass is the one point where gravitational force acts. And that's kind of going to be the greatest tie-in with future sections in this chapter when we talk about, systems that are rotating, things that have gravitational torque like rolling balls. The center of mass is that one point where the gravitational force is applied. Because before it didn't matter where gravitational force was. It was just a vertical force, right? Depending on if we had a tilted coordinate axis or not. And that was it. It was just a force. And we summed it up with other forces, potentially took components of that gravitational force, but its location was completely non-consequential, okay? But here it does matter, okay? It absolutely matters because we're going to be talking about rotation. Maybe we're going to be pivoting about that center. Maybe we're going to be pivoting about some other center, and the gravitational force acting at the center of mass is going to create a torque about that other pivot point. But we'll see that all in practice. If it doesn't make sense now, that's totally understandable. Let's look at our key formulas, all right? So here we're just going to focus on solving for the center of mass. We'll relate it to other ideas in future sections, okay? So this formula right here is XCOM. That would be the center of mass in the X direction. It is represented by the summation symbol here, all right? 1 over m, big M, is the total mass. This summation represents summing individual masses. So this would be for discrete particles, which is like a countable number of particles. So like particle 1, its mass and its x location, its x coordinate, right? And then we could say have particle 2 and its x coordinate. And then we're just going to be summing however many particles there are, or balls or objects or whatever, from 1 up to the end, whatever that final number is, which is the total number of objects, particles in our system. Let's see kind of what that looks like specifically for n equals 3. We'd have our total mass just being m1 plus m2 plus m3, because that, of course, obviously is the sum of all the masses. And then our summation is m1x1 plus m2x2 plus m3x3. So you can really see what that summation symbol looks like when it's put into practice for an n equals 3. Okay, which is good because otherwise I know the symbol can be a little bit confusing. And it's the same exact idea for the y center of mass and the z center of mass. No difference. It would just be along different axes and considering the contributions of mass and location along those other axes. And sometimes you might want to define a center of mass vector. So this would just be the displacement from the origin to the center of mass. So this is RCOM, right? So it's just a displacement vector pointing from some point, usually the origin, to the center of mass, all right? And this would just then be the XCOM times I hat, YCOM times J hat, and so on, right? Just the components of that R vector, okay? And we'll see that in one of our examples. And our final idea is a bit different. It is the idea that the center of mass has a particular velocity, and that velocity can be found by just considering the total momentum of the system divided by the total mass of the system. So essentially, the V comm is P total over M total. All right? So for two particles, it'd be P1 plus P2 over the total mass, M1 plus M2. The initial here isn't that important. It's just showing that's the initial momentum. I could have really left that with just subscript 1 and 2. Okay? All right? And of course, that is a vector. So essentially, that's telling us an important idea that we've seen before. It's telling us that if the momentum doesn't change, then their center of mass cannot change. So for isolated systems where there's no external forces and where the translational momentum is conserved, the velocity of the center of mass must be 0. Okay? All right, but we'll see that. Okay, so two types of problems. Problems that involve finding the center of mass for a system of discrete particles. Discrete particles just means, like not a solid object. Okay, so that would be like, 3 balls, for example. They're discrete, they're separable. All right. The other type of problem we're going to see in this section is problems that involve finding the velocity of the center of mass of a system, or using the known center of mass velocity to find displacements of individual objects. Okay, so either one way or the other. All right, let's look at our first example. So shown is a simple model of a water molecule. The oxygen-hydrogen separation is 9.57 times 10 to the negative 11, right? Just under 1 angstrom. And that's that distance right there. That's our D. Okay? All right, each hydrogen atom, and that's center to center, because that's the way we do this, right? When we talk about center of mass of an entire system, we consider the coordinates of the centers of each of the discrete particles. Okay, here we have 3 discrete particles, 1 oxygen, 2 hydrogen. Okay, each hydrogen atom has a mass of 1 atomic mass unit, 1 U, and the oxygen molecule has a mass of 16 U. Find the position of the center of mass. 1 atomic mass unit, U, is 1.66 times 10 to the negative 27 kilograms. Okay? All right, so how do we go about doing that? Well, we just want to find each part individually. All right, so we want to first consider this angle. So we're told that the overall angle between the 2 hydrogen particles is 105 degrees, which means the right triangle that I'm going to consider for purposes of coordinates has an angle there, theta, of 105 over 2. All right? Right, which is just going to be 52.5. All right? Okay, so then we're going to consider the x coordinate of the center of mass. How do we go about doing that? Well, it's 1 over total mass, and then the 3 particles. All right, this is just going to be the x coordinate of each of the particles. Our xy coordinate system is already shown in the figure, and the origin is located at the center of the oxygen molecule. Thus, the x coordinate of the oxygen molecule is 0. That doesn't mean that the molecule doesn't contribute to the center of mass. Of course, it contributes largely to the center of mass, since it is 16/18 of the total mass of the system. But that value shows up here in the denominator. It essentially pulls it towards 0. So it's kind of interesting. Even though this part zeroes out, the effects of the oxygen mass still show up right there in M total. And then we just look at the coordinate and the mass of each of the oxygens, dxMH and dxMH. Okay, dx again is this vector right there, all right? Or that displacement in the x direction. Thus, the coordinate of the center of mass in the x direction is 1 over M total times 2 dx times mh, right? There it is. There's the overall effect, okay? Moving on to y. Well, we look at y, and the center of the oxygen molecule is going to be at 0, so no effect there. And let's even look a step further at the 2 hydrogens. Well, the hydrogens here are equal distance away from the x-axis. Thus, their y contribution to the center of mass cancels out. So then we can confidently say that the y center of mass is 0. We could have reasoned that out, but the equation certainly confirms our reasoning that, of course, because of symmetry, the center of mass must be balanced or right along the x-axis. Okay, so moving right along then, we can then consider that the x center of mass is our entire center of mass in terms of the coordinate, and we'll just plug in our actual numbers. Here is our 18 atomic mass units, because 16 for the oxygen, 1 each for the hydrogens. Here is the contribution with the angle as well of the hydrogens, and then we see that we're then going to, and there's the actual mass of the hydrogen, right? And that's the distance, by the way, that we're just into 1 angstrom. And so then there's our actual effect, 6.47 times 10 to the negative 12. So considering that this is less than 1/10 of D, so x comm is less than 1/10 of D, it would be rather close. It'd be kind of right at that point. And if you look real carefully, you can see that there actually is an x that I drew over at the purple line. That is actually the center of mass. So the center of mass is not quite at the center of oxygen, but it's pretty close. Okay. Now that matters though. That absolutely affects the way the molecules behave. They wobble relative to the center of the oxygen, so they don't perfectly spin about the center. Instead, they wobble about that point. Okay. So moving right along to another similar example, but with 3 particles and not related to any particular molecule. Okay. So here are the things we're going to want to consider. I'll just put them in the figure and read the problem. So example 2, shown is a system of 3 particles. The masses are M1, 12.65 kilograms, M2, 9.44 kilograms, and M3, 19, the biggest. The displacement vector for M1 and M2 relative to the origin both have magnitudes of 3.334 meters, okay? And that would be the distances here, this one, and this one, all right? And the displacement vector for M3 relative to the origin is given. It's a bit longer. It's 4.008 meters. That's this one right here. All right. The angle that R3 makes with the negative x-axis, that's this angle theta as shown, is 28.79 degrees. So you have all our information. It's just a matter of finding our center of masses. So what is the magnitude of the displacement vector of the center of mass relative to the origin? So we just want to find the length of RCM. So RCM is going to be right here. So you can kind of already show you the answer here a bit. It's going to be rather close to the origin. So it's the system isn't quite balanced, but it's nearly balanced relative to the origin. The reason it's not quite balanced, of course, is because M3 is more massive and it's slightly further away, which pulls the center of mass down into its quadrant, so to speak. Okay, but it's still fairly close to the origin, so it's going to be a much smaller displacement vector than R2, R1, or R3. Furthermore, the angle here is quite small. That's the angle beta. That's going to be relevant for part B. Let's go ahead and solve for part A just using the formulas. All right, so we're just going to do x center mass and y center mass. So let's work through both of them. It's simply a matter of just summing up all the M1 x1s, M2 x2s, M3 x3s, and dividing by M total. All right, so it's the same every time when you do a center of mass. Then we do the same thing for y. We're not going to have to worry too much about some of our coordinates here because x2 is along the x-axis, so it has a x value of 0, and then x1 is along the y-axis. So we have one thing 0 out in both cases, which only leaves us 2 terms in each numerator. Our denominator is the same in both cases. It's just the total mass. All right, so then when we go ahead and solve for that, we're going to get for xcm, it is negative 0.607, and for ycm, it's also negative 0.133. Again, notice these are quite a bit shorter than the lengths of many meters. Instead, we have lengths of just less than a meter, 13 centimeters and 60 centimeters. So then our overall length is 61.4 centimeters or 0.614 meters. All right, that's our overall length of RCM. Okay? Okay. And it kind of makes sense to have it be about that short because remember, after all, this has a length of 4. So that means that this length here is about 1/8 of the overall length of this black vector. Okay? So there we go. That's our magnitude. That is our answer for part A. For part B, we're simply asked a question about components via an angle. We're asked what angle does RCM make with the positive y-axis. That would be the angle phi shown here. I always find it easiest to find the angle relative to the closest axis, which would be beta. And since I wasn't asked for the angle relative to the closest axis, which would be the negative x-axis, I just add however many degrees that is necessary to get to the desired axis, in this case, the positive y-axis. So in other words, the angle I'm looking for phi is just going to be beta plus 90. So let's find beta. All right, so then beta is just going to be ycm over xcm. Why is that? Well, if you zoom in, that's just opposite over adjacent. Y is the opposite, x is the adjacent. All right, so that's going to give us our beta angle, which is 12.4 degrees, small, just as shown. So that means phi, the desired angle, is just going to be 90 plus 12.4, or 102 degrees. All right, 0.4 degrees. Okay, one too many sig figs, but we'll let it pass. Actually, no, it's the right number because we had 4 in each case. All right, okay, so we actually were missing a sig fig there. But there you have it. There is the approach, pretty straightforward, just using the formula and then, if necessary, doing a little bit of trigonometry. Okay? So let's do a quick concept question here. A machinist starts with 3 identical square plates, but cuts 1 corner from each of them. 2 corners, or 1 corner from the first one, 2 corners from the second, and 3 corners from the third. All right, so it's not 1 quarter from each. Although I guess it would be, but then it's just, then you add some more to the other ones. All right, so anyway, you can see in the picture clearly, we cut 1 corner from the first, 2 corners from the second, and a total of 3 corners from the third. And rank the 3 plates according to the x coordinates of their center of mass from smallest to largest. Okay, well, let's think about it here. All right, here the center of mass is going to be more in the positive direction, right, because there's less mass on the negative side. Here it's going to be even more in the positive direction. right? Because now there's even less mass in the negative x side. And then if we look here, what about number 3? Well, number 3, we definitely have some loss of mass on the negative side, but then we also have some loss of mass on the positive side of the y-axis, in other words, the positive x direction. And that means that these two corners would cancel out their effect in terms of the x center of mass, because after all, we're only looking at the x coordinate. So then it's only this one corner that's pulling the center of mass in the positive direction. So that means that actually 1 and 3 should be tied, all right? So 1 and 3 then should be the least in terms of their actual positive value of x, and 2 will be the largest value of the x center of mass, because the x center of mass in this one will be pulled way over here. This might be the com, whereas the com would be closer to the origin for the other two. Okay? All right, so there is our ranking from least to largest in terms of the x value of the center of mass. Okay, hopefully that makes sense. Now let's do 2 examples to wrap up this lecture involving the velocity of the center of mass. Okay, so this one is just going to be about finding it. All right, so at the same instant that a 0.5 kilogram ball is dropped from a 25 meter height above Earth, a second ball with a mass of 1/4 kilogram is thrown straight upward from Earth's surface with an initial speed of 15 meters per second. They move along nearby lines and pass without colliding. At the end of 2 seconds, what is the height above Earth's surface of the center of mass of the 2-ball system, and what is the velocity of the center of mass of that system? All right, so this is the picture here. We've got our 2 balls. At the point taken, which is after 2 seconds, ball A, that is the one that was dropped, is actually lower. It's already past ball B, and ball B is already higher. So they've already passed each other. Ball B is on its way up. Ball A is on its way down. B has not reached its highest point yet, but it has slowed down significantly. And we would find this all of kinematics. In fact, let's go ahead and do that. So at 2 seconds, we'll just then plug it in. And notice all the mention of Earth. That's just to tell us that gravity is G, and we have no concerns there. Okay, and it's a constant value. It's just 9.8. Okay, meters per second squared. So for kinematics, then for A, since we have some initial height of 25 meters, then our final location is just going to be that height minus however far it's fallen. It hasn't reached the ground yet. I made sure that 2 seconds was not ground. Likewise for B, maybe similarly for B, it started at the ground, but it's on its way up, and then gravity is slowing it down. All right, and then we don't have to solve for t anything because we're given t, but there is an initial velocity, whereas there was no initial velocity for ball A. But anyway, then we find that here we can find its height. So then we go ahead and find that. We find A is at 5.4 meters, so it's most of the way to the ground. It's already covered almost 20 meters of distance on its fall. And meanwhile, B, that started at the ground, is at a height of 10.4. It's almost reached its maximum height. All right, but anyway, that's where we're at. Okay, so if you want to find the center of mass, we'd simply find the center of mass in terms of the height. We're only interested in the y direction. These should really be y's. I don't know why I wrote them as x's, but the value will still be correct. All right, and this is a one-dimensional problem, so there's nothing to worry about in the x direction. And so then when we actually plug in our 5.4 meters for A, the mass of A, our 10.4 meters for ball B and its mass, and then divide by the total mass. All right, and there should be kilograms there. Then we find, there we have it, our height of the center of mass of the system, 7.07 meters, okay? And again, that's a big contribution there, is they're not equal mass balls, and so that pulls the center of mass, lower than it would be otherwise, okay? Because otherwise it would be a bit closer to the 10.4 if they're equal mass, okay? It'd be more like 7.5, right? So there we have it, 7.07 meters, the center of mass at that particular moment. But that center of mass does not remain constant in this case because there definitely are external forces here, gravity. And so that means that the velocity of the center of mass will be non-zero, and let's see what it is, all right? So we can find the velocity of A, which is simply going to be, at this particular moment in time, 19.6 meters per second. All right, that's the one that's almost on the ground, which is why it's sped up quite a bit. And the velocity of B is much slower because, again, it's reaching its maximum height and has a velocity of negative 4.6. It's already on its way back down? Okay, so VB is actually on its way back down according to this, because 920, yep. So this should be in this direction. I'll fix that when I upload the notes. So B is still higher than A, but what I forgot to check when I drew this picture quickly was my number, which I'd already solved for. I forgot that B has actually already reached its maximum height and is on the way back down. It's just that A is still lower and it hasn't hit the ground yet. So you imagine that they passed, so A and B passed some half second earlier. B reached its maximum height up here and is already on its way back down. So the only thing that's wrong here is that VB vector should be drawn down. Okay. So let's do the correct numbers here, despite the little mix-up there in the picture. Then the velocity of the center of mass we can simply find by plugging values into the formula. All right, so plug in the mass. Make sure to plug the negatives, because that's going to matter. Our velocity, after all, is a vector, and in this case, it's the one-dimensional vector, but it still can point up or down. All right, and in this case, it's obviously going to point down because both the velocities point down. And there we find it. Our velocity of our center of mass is negative 14.6 because at this point, everything's moving in the downward direction. There would be some moment, by the way, like a half second or a second earlier, where the velocity of the center of mass would be 0. There certainly would be a balance point. Okay? All right. So now, instead of just finding the velocity of the center of mass, let's use it to find something else. So this will look kind of similar, right, to problems you've seen before. This is the case of a movable ramp. So the idea is that as the ball, in this case, it could be a block, pushes on the ramp, there'll be a contribution of, well, I guess there'll be a normal force. There'll be a normal force that pushes in this direction. There's a component of that normal force, F and X, that pushes the block that causes it to accelerate, or the ramp. So the ramp accelerates as the ball pushes on it and also as the ball slides down the ramp. And of course, it's the whole idea this is not a fixed ramp. And it's a fairly complicated system. We have to find consider all the forces, do a full force diagram with different coordinates, and then eventually find the acceleration of the ramp. Once we have the acceleration of the ramp, then we can find out how far it moves in a certain amount of time. Because that's basically the question here. A ball with a known mass is at rest on a frictionless ramp. We know the slope of the ramp, and we know the mass of the ramp. The ball is positioned directly above the center of mass. Okay, so that's going to be the idea, is that the center of mass of this ramp is close to the corner, but that is its center of mass, okay? And that would just be due to some unequal density distribution, but we don't care. It doesn't affect the problem, all right? And if the ball is released from a height of 27 centimeters, how far will the ramp slide along the frictionless ground? Because that's the whole idea. The ramp is movable, okay? So my point being is that we could solve this problem by finding the acceleration of the ramp with a Newton's second law, F net equals ma approach, and we've done that. And then once we find the acceleration of the ramp, then we can simply find out how much time it takes for the ball to go all the way down, how much time it takes to cover that distance based on basically the parallel component of the ball's acceleration relative to the ramp angle. And once we have that time, then we can plug that time back into kinematics for the acceleration, the constant acceleration of the ramp, and there we go, we got distance. But that's a lot of steps. And it turns out that we can cut out many of those steps by using instead a velocity of center of mass approach, which really is a conservation of momentum approach, but does have its limitations. Because notice what I'm asking here. How far will the ramp slide? Well, momentum and center of mass are very good for answering questions about distance. If I was to answer or ask a question about time, by the way, we'd have to go back to the more difficult approach by doing a full free body diagram. But here, since we were only asked about distance, we can get away with just using the velocity of the center of mass. Okay? All right, so here we go. Since there is no external force, see, very much of a momentum idea, the velocity of the center of mass of the system must be 0. V com equals 0. That's true anytime there's no external force. And there is no external force in the system. All the forces are internal. So then we have, by definition, the velocity of the center of mass is Pm plus P little m plus big M, and then little m plus big M is in terms of the total mass. We know it's 0 because of the lack of external forces. And so then we just go ahead and rewrite the two momentums as little m and the velocity of little m, that's the ball, and then mass of the ramp times the velocity of the ramp divided by the total mass of the system. All right, then I'm just going to rewrite this. Since the denominator, we can just multiply it by 0 and it goes away. Then we only care about the numerator. I'm going to rewrite both the velocities in the numerator as just displacement over time. All right, and so then when the times are going to cancel out, and so then we can simply consider that we then have xm equals, and this is just the definition of velocity, okay? And then we just have xm equals, and it would be average velocity, by the way. All right, so really this is average velocity. That's fine, because average velocity is going to get us the number that we need, okay? And I say it's average because they are accelerating, but we don't care about the acceleration. We only care about the displacements, okay? And so then we're going to find the x big M, all right? That's what we're asked for, all right? And then that's just going to be equal to the mass of the ball times the displacement of the ball divided by the mass of the ball, all right? We don't have the total mass anymore because remember we multiplied it by 0. Okay, and do we have the x displacement of the ball? Well, we do. We just have to do a little bit of trigonometry because we were given the height and we were given the length of the angle of the ramp. So given the height and the angle of the ramp, we can absolutely find this angle here. So essentially what we know is we have a right triangle like this, and we know we basically know the angle, and we know one side, we know h, and then we just need to find the other leg. We don't care about the hypotenuse in this case. All right, so I'm just going to go ahead and do that. I'm going to replace xm with h over tangent theta, and that's just from this, okay? And that's just solving for xm. I just cross multiply. All right, and then we just plug in all our values, mass of the ball, the height of the ball, tangent of the angle of the ramp, and then divided by the mass of the ramp. And there we have it. We have that the ramp slid backwards, that's what the negative represents, 12.5 centimeters or 0.125 meters, all right? And that's in comparison to however far the ball goes, which would be a pretty significant component of 27. So obviously the ball goes further because it's less massive. Okay, so that is a much simpler way of doing it than doing sum of forces and kinematics, okay? And by the way, we could have totally done this problem back when we did our conservation momentum system, or types of systems that would involve conservation momentum, like recoiling, because this is basically a recoil problem. The ball pushes on the ramp pushes on the ball, Newton's third law, and the ramp recoils backwards. So there's a lot of ways to approach this problem, but we're at that point in terms of presenting this material where we have different tools in our tool belt. This center of mass approach hopefully makes a lot of sense and certainly saves us some mental effort. Okay, well, I hope our introduction to center of mass has been interesting. Mostly this is going to be a type of problem that's going to be applied to other problems. It's going to be part of other solutions, but it does stand on its own. And thank you so much for watching this video.